We say a matrix A is similar to a matrix B if there exists a non-singular matrix P such that B is equal to P inverse times A times P. If a matrix A is similar to a diagonal matrix, then A is said to be diagonalizable, or that A can be diagonalized. If A is similar to B, then A and B have the same eigenvalues. To see this, what we're going to do is show that they have the same characteristic equation. All right. So characteristic equation for B is the determinant of lambda I minus B. And since A is similar to B, we can say that this is the determinant of lambda I minus P inverse times A times P. However, this is equal to the determinant of P inverse times lambda I times P minus P inverse times A times P. Right, and this is because if you multiply by the identity, multiplying by the identity matrix is commutative. So now what we can do is we can say, well, look, we can factor out a P inverse on the left. We're left with lambda I minus A. And then factor out a P on the right. And then properties of determinant say this is the determinant of P inverse times the determinant of lambda I minus A times the determinant of P. Right? How to determine P inverse? 1 over determinant of P. So we wind up with the determinant of lambda I minus A as desired. Let A be an n by n matrix. A is diagonalizable if and only if it has n linearly independent eigenvectors. Right, so first, by definition, there must exist a matrix P and a diagonal matrix D such that P inverse times A times P is equal to D. And we can rewrite this by multiplying by P on the left as AP is equal to PD. Right? What we can do is specify columns. Of P and entries of D. right? It's giving us this equation. A times U1 up through UN, where each of these U's are column vectors. And this is equal to, again, same column vectors, now times our diagonal matrix, right, where each of the elements on the diagonal is some scalar, column lambda 1 through lambda n, and everywhere else is 0. No, I'm not going to put those arrows, just write them as zeros. Okay, now we can rewrite this. The equation is this. And that's simply by performing matrix multiplication. Right, and in order to be equal, we have to have AUI is equal to lambda UI, right, for all I equal to 1 through n, right? But this means that A has n linearly independent eigenvectors. Conversely, assuming that A has n linearly independent eigenvectors, column U1 through UN associated with the eigenvalues lambda 1 through lambda n. We must have that A times UI is equal to lambda times UI for all I equal to 1 up through n. What we thus have is this. If we set P to be the matrix with columns U1 through UN, and D as the matrix whose diagonal elements are the eigenvalues, we see that P is non-singular, meaning it has an inverse. And so we have AP equals PD, which implies that P inverse AP is equal to D as desired. If lambda 1 through lambda n are distinct real eigenvalues of the matrix A, then the corresponding eigenvectors x1 through xn are linearly independent. We will do this by contradiction. So what we will do is assume that x1 through xn are linearly dependent. Now, since x1 cannot be the zero vector, it follows that at least one of x2 through xn can be expressed as a linear combination of the preceding vectors. Right, so let xj be the first. Such vector. Then AXJ is A times C1x1 plus so on and so forth plus CJ minus 1 XJ minus 1. Right, by properties of matrix operations, this becomes C1 AX1 plus so on and so forth plus CJ minus 1 A times X J minus 1. However, since each xi is an eigenvector, what we now have is lambda sub j, x sub j is equal to c1 lambda 1 x1 plus some sort of plus cj minus 1 lambda j minus 1 x j minus 1. However, we also have lambda j x sub j equals c1 lambda j xj. I'm sorry, x1 plus so on and so forth plus cj minus 1 lambda j x j minus 1. Oops. Subtracting yields that 0 is equal to c1 times lambda 1 minus lambda j x1 plus so on and so forth plus cj minus 1 lambda 1 minus I'm sorry, lambda j minus 1 minus lambda j times x sub j minus 1. Right? Since eigenvalues are distinct and x1 through xj minus 1 are linearly independent, we must have C1 is equal to C2 is equal to so on and so forth equal to Cj minus 1 all equal to 0. Which would mean that x sub j has to equal 0. Which means that x sub j would not be an eigenvector. This is a contradiction. Therefore, the eigenvectors x1 through x sub n must all be linearly independent. A direct corollary of both Theorem 2 and Theorem 3 combined is that if all the roots of determinant of lambda I minus a are real and distinct, then a is diagonalizable. We will now determine matrices P and D such that for this matrix A, P inverse AP is equal to D, where D is diagonal. And this must be a mistake because this is not example 2. This is our first and only example. Well, based on the work so far, what we need to do is determine eigenvalues and then our linearly independent eigenvectors. All right, so recall to determine eigenvalues, first we must set up our characteristic equation. All right, so determinant of lambda I minus a. This is equal lambda minus 4, 2, negative 1 is the first column, negative 1, lambda, negative 1 is our second column, 3, negative 2, lambda as our third column. And these should be determinant bars. Taking this determinant, we will get lambda times lambda squared minus 4 lambda plus 3 is equal to 0. Solving this will give lambda 1 equal to 0, lambda 2 equal to 1, and lambda 3 equal to 3. Right. So for the first one, lambda 1 equal to 0. We get this matrix. When we row reduce it, this is what we get. this gives us our first eigenvector, our first eigenspace, right, I should say, as the set of all vectors of the form r, negative r, and r. Now we can pick any vector from there. So let's just set r equal to 1, and we get our eigenvector of 1, negative 1, and 1. For lambda 2 equal to 1, we'll get the matrix. Which, when row reduced, will give us which means our second eigenspace is the set of all vectors of the form r, 0, r. Setting r equal to 1, we get 1, 0, 1. Right, and I should specify in both of these, right, r can't be 0. No, I'm sorry, r can be 0. Right, because the 0 vector has to be in the eigenspace. And then for lambda 3 equal to 3, we get this matrix. Which, when row reduced, will give us so this implies that the third eigenspace is the set of vectors of the form 7r, negative 4rr. Setting r again equal to 1, we get the eigenvector 7, negative 4, 1. Right, so by theorem 3, these three eigenvectors that we found are guaranteed to be linearly independent. And so we take our P to be the matrix where each column is the associated eigenvector. Right, so the first column will be the first eigenvector, which we said was 1, negative 1, 1. Second column will be the second eigenvector, 1, 0, 1. And the third column is the third eigenvector, 7, negative 4, 1. And we take as our diagonal matrix the matrix whose main diagonal elements are the associated eigenvalues. So the 1, 1 entry would have to be 0. the 2 2 entry would have to be 1, and the 3 3 entry has to be 3.